All right, it's likely that you've seen Venn diagrams in your life. We're going to study them a little bit, and I want you to remember this set right here, the natural numbers. They just went 1, 2, 3, and dot, 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 as that went on forever. And then I'm going to pick a set so you see that A is completely inside of N. So A is contained within the natural numbers in symbols. We write that A, that symbol right there, is a subset of the natural numbers. Now, a lot of times it's helpful to draw a picture of relationships among sets. So let's go ahead and draw a picture of what this might look like. So typically you make some sort of a square, and here you use the letter U to represent something called the universe. We'll talk about that in a minute. But in this problem, my universe is the set of natural numbers. And then A is just some sort of a subset inside of there. This is a way of visualizing that A is inside of the natural numbers. And you can even add, if you want to, some shading if you want to indicate that I'm talking about the set A. Now next, consider these integers. They look like this: dot, 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 -3, -2, -1, 0, 1, 2, 3, and it went on forever in both directions. So it contained all of the positive and negative natural numbers with the addition of 0. Here, let me put the natural numbers up again. They simply start at 1 and go on forever. And we can see that the natural numbers are a subset of the integers as well. So in this situation here, we might draw a Venn diagram that looks like this. Here, our universal set may be the set of integers, and then we could have a circle with the natural numbers inside of it. If we're talking about the set of natural numbers, then maybe I'll shade it. U is called the universal set, and it varies from problem to problem. So as you see in my first two examples, the universal set was the natural numbers in one example, and then it was the integers in another example. U contains everything under consideration at the time. So in many of these pictures, we will use shading to denote a set. Let me draw another set for you. An important type of set that we should consider is called the complement of a set. And the way that looks is the following. It's the set of all items X such that X is in the universal set, but X is not in A. So these are all the items that are specifically not in A. So if I wanted to represent the universal set, the complement of a set, what I might do is draw A and shade on the outside of it. And then we always put the universal set somewhere up in the corner to indicate what is the universe we're dealing with at the time. So here's a picture of essentially everything that's not inside of inside of A. Let me do some examples to illustrate this. So in this problem, let's let U be the following set. We'll have U equal to the set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we'll let A be the odd numbers. So A will equal 1, 3, 5, 7, 9. And so A prime, or the complement of A, should be all the items that are in U that are not in A. So let's take a look at those. If I start with all of the items inside of U, and start taking out all of the items that are in A, I take out the 1, the 3, the 5, the 7, and 9. I'm talking about the numbers that are left over is exactly what the complement of A is. So we'll have 2, 4, 6, 8, and 10. I don't think I put the word down. Let me come back to the definition. This is called the complement, C-O-M-P-L-E-M-E-N-T of A. So this is important, and it has some uses for solving various problems that you'll see later on. Let's try another U. U will equal X such that X is a letter in the English alphabet. So we know that U has 26 letters. A will be the set of all X such that X is a consonant in the English alphabet. So if I want to do the complement of A, the non-consonants in the English alphabet are precisely the vowels. So I can actually list it this way: A, E, I, O, and U. And I'm not assuming that Y is a vowel as usual. So the set of all non-consonants is what A prime is. A couple of notes. These are more for, I don't know if you'd call it technical reasons than anything else, but we'll have need for these. If I take the complement of the universal set, it will equal the empty set. If I take the complement of the empty set, it will equal the universal set. Now, we've talked about subsets before a little bit, but let me go and write it in more detail, I think, than I did in the past. A is a subset of B if every item in A is also in B. And if that's true, we write A and this symbol, then B. So that means that A is a subset of B. A couple of notes. No matter what set A is, there's two things that we know to be true of it right off the bat. One is that the empty set is always a subset of it, and that it is always a subset of the universal set. Now let's do a concrete example, and let's see if we have 3, 2, 1, 0. That's going to be a subset of -3, -2, -1, 0, 1, 2, 3. That's pretty easy to see as an example. Pictures. If I have something like A is a subset of B, when I draw a picture of the situation, I might draw like this. B here, and then I might put A inside of it. Don't forget your U up in the corner, though. Let's let U this time be the days of the week, but I'm just going to write it with letters. So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and then Sunday. So Sunday gets the S, Saturday gets the A. All right, let's do A is equal to, let's just say Monday, Wednesday, and Friday. And then let's say B is equal to Monday, Tuesday, Wednesday, Thursday, Friday. So here's my sets. Notice then that A is most definitely a subset of B, because everything inside of A is also inside of B. However, notice that A does not equal B. So that means there are items inside of B that are not in A. For example, let's see, 2T is not inside of A. What else is not inside of A? Thursday is not inside of A. Because of that, we know that B is not a subset of A. So what we have is this. We have that A is a subset of B, but A does not equal B. So we can actually refine our symbol to this. A is what's called a proper subset of B. So we can now write any of the previous things that we did where I had a line under them. You don't have to have the line underneath of the symbol if the subset is not equal to the set that contains it. All right, let's pick another U. A, B, C, D, E, F, G. And let's let A equal simply A, comma, E. Let's let B equal A, B, E, F, G. C will be B, F, G. And D will equal D, E. Now let's take a look at what things are a subset of other things. So let's start with the letter A. Is A, well, no, I don't want to put a line under it. I don't know if I should put solutions either because I haven't even asked a question, but I do want to write a bunch of stuff. So A, you'll notice that all of these things, A, B, C, and D, are all subsets of the universal set. That's always going to happen. However, I want to look and see which ones are subsets of each other. So if I look at A, it contains just the letters A and E. Now, who else contains those letters? I see that B contains an A and E. So I automatically have that A is a subset of B. And since A doesn't equal B, I can even use proper subset notation. Is A a subset of anything else? So if I look at this, it's certainly not going to be a subset of C, and it's certainly not going to be a subset of D. But I do notice if I look at C, BFG is inside of it, and I notice that BFG is also inside of B. So I have C is a proper subset of B also. By the way, it's okay to write A is a regular subset of B, because having the line under there simply means that you're allowing for the possibility that the two sets are equal. Only when you know that the two sets are not equal should you use notation like proper subset notation. So in fact, it's okay to do this. For any set, A is a subset of A, but A cannot possibly be a proper subset of A because A equals A. Some other things I can throw in here. Let's do the complements of each of the sets. So A prime, remember you're looking at U to tell you what's in A prime. So what you can do, if you want to start with U, like A, B, C, D, E, F, G, and then just go and look at A and cancel out the items that are in A, and what's left over is your complement, B, C, D, F, G. Complement of B. So if I do A, B, C, D, E, F, G, let me wipe out all the things that are inside of B. We have an A, B, E, F, G. So what's left over is C, D. Got that. C prime. I have A, B, C, D, E, F, G. And let's wipe out the things that are inside of C. That would be B, F, and G. So that leaves me with A, C, D, E. And last but not least, I'm going to do D, complement of D. And all I have to do is write, I'm not going to do it like the previous ones. I'm going to do this in my head. So I know that I can write the letter U, A, B, C, but I know I got to skip D and E, and then I'll put F, G. So you can probably do it in your head without having to write a lot. Now, another thing that we concentrate on is, since we're talking about subsets, we're going to want to talk about the number of subsets of a given set. For set A, we already know that the empty set is a subset of A, and A is a subset of A. So in most every case, when you start counting up the number of subsets, you're automatically going to already have at least two. But we're going to do an example to show how to get the rest of them. So let me do this. We'll start easy. Let's let my set be an item, or a set with just one item in it. That's all. How many subsets does A have? Well, let's take a look. We know we've got the empty set and A itself. Are there any other ones? Well, if I look, if I try to just do this one here, I've already done that. That's A, so I'm not going to count that one. So that's it. I just have two of them. So 2. Recall that the empty set has 0 items in it. How many subsets does it have? Well, there's only one. It's the empty set itself. So the only one that you're going to have is that, because any other set is going to have items in it, and it's obviously not going to be contained in a set that has no items. So it has exactly one subset. Let's move on. I'm going to do a couple of cases, then we'll get to the formula. Let's let B equal AB. How many subsets does B have? Well, let's take a look. You always got the empty set and B itself, so there's two of them. Now let's see what else we can have. We could have this. A all by itself would be a subset of B. We could also have this. B all by itself is a subset of B. Now I can't do AB because that's already B itself, so I have exactly 4 of these things. Let's move on. Let's let C equal A, B, C. How many subsets does it have? Well, once again, we have the empty set and C itself. Now, the way you want to count up subsets is I might as well take a look at the sizes of the subsets I'm talking about. So far I've taken care of 2 subsets. Now the proper subsets that I want to have include sets that have 1 item in them. So I'll have 3 of those. That will be 1 subset of 1 item, a second subset with 1 item, and a third subset with 1 item. Now since this set has 3 items, I also have subsets that have exactly 2 items in them. So here's another subset, A comma B. And then I have A comma C. But then I'm going to have B comma C. So if I count up all of these subsets, remember I don't have any subsets that have 3 of them to count because I've already counted them when I did C. So let's count. 1, 2, 3, 4, 5, 6, 7, 8. Now, to make use of what we did in the first section, I believe, we're going to take a look and use inductive reasoning to come up with a solution to this problem. So what we had was the cardinality. Let me put that in. The size of the set. So when it was the empty set, how many subsets did we have? So when we had the empty set, the number of subsets was 1. When we had 1 item in the set itself, we had 2 subsets. When we had 2 items in the set itself, we had a total of 4 subsets. And then we had 3 items, we had a total of 8 subsets. And the trick here is to realize that the number 1 is equal to 2 raised to the 0 power. The number 2 is 2 raised to the first power. The number 4 is 2 raised to the second power. And the number 8 is 2 raised to the third power. It shouldn't be hard to see what's going on here. Whatever the cardinality is goes into the exponent. The base of this thing is always going to be 2. So now, using inductive reasoning, I'm going to do this. If the number of items in A is equal to the letter N, whatever that letter is, then A has 2 raised to the nth power subsets. So there's our formula. Now when you're counting up all the subsets, one of the subsets we always count is the set A itself. If you take away the set A, then all of the subsets left over are proper subsets. So that means if 2 to the n is the total number of subsets, you subtract 1 to get the total number of proper subsets. So 2 to the n minus 1 is the number of proper subsets. Quick example, how many proper subsets does A have? So since the number of items in A is equal to 4, A has 2 raised to the 4th power, which is equal to 16 subsets. While you're at it, you can answer the number of proper subsets really easily. A also has 15 proper subsets. How many subsets does B equal 1, 2, 3, ... up to 10 have? And the answer to that, we have 2 raised to the 10th power, which equals 1024. We have 1023 proper subsets. Consider this set E, which I'm going to put it in set builder notation. We're going to have, it's the set of X such that X is a non-negative even integer less than 4. How many subsets does E have? Well, first, let me get an explicit reading of what is in E. I'm talking about non-negative even integers. Well, the first non-negative even integer is 0. The next one after that is 2. And we have to be less than 4, so I have to stop there. Well, then this is easy. That just has 2 items. So we have 2 raised to the 2nd power, which equals 4. That's the number of subsets. We have 3 proper subsets.